Pereira. I'm a PhD student here in Portugal, and I've been working with essentially using visual scenes and interpreting their information and transiting it to more advanced representations and eventually the synthesis of scenes. So the title of this work is A Transition Towards Virtual Representations of Visual Scenes, and I'll start by outlining essentially what I'll be talking about in this presentation. So I'll start by introducing the initial topic and the area essentially that is an umbrella where this is present. I'll also talk about what motivates this work and essentially talk about what we propose as an idea of an architecture that can help this transition from a visual scene to a virtual representation. We also presented a proof of concept that shows that this proposed architecture can also be used in practice, and we have some results about it. And we believe that this can lead to some interesting new researches opportunities that could even elevate even more this work. So starting with the umbrella topic that is visual scene understanding. Well, in practice, some researchers use the essential definition that visual scene understanding is basically obtaining semantic information from the scene. And for instance, algorithms such as semantic segmentation are used as a definition of visual scene understanding. However, we believe that this is a bit different because this is more of an umbrella that essentially all information from the visual scene and all algorithms that extract information from the visual scene can be seen as being part of visual scene understanding. So we see visual scene understanding as a fundamental task that aims to extract meaningful information from visual data. Essentially, another thing that happens is that there are multiple ways to extract information from visual data, and there are multiple types of algorithms. And this means that depending on the type of data that you want to extract from the image, you have multiple different options. And this leads to a disjoint and specialized algorithms that are specifically tasked or tailored for those specific applications. So here we have an example. On the left, we basically have the detection of humans, where we have and objects, where we have bounding boxes, which this could be used, for instance, to count the amount of people that are on the bridge and so on. And on the right, we have another vision algorithm that basically does the semantic segmentation of an image that can be used, for instance, to know what is the percentage of the image that is grass, for instance, or something like that. So those are completely different approaches with completely different algorithms that also use visual data. So this leads to what we see as a fragmentation of different types of algorithms in this area. And this could be a bit problematic when we try to create a more complex system that integrates multiple types of scene analysis algorithms that are then or can then be integrated in a complete system that basically extracts all the meaningful information that is needed from the scene towards other possible final applications. So another problem that exists is kind of the inexistence of standards. For instance, in this previous image, we have bounding boxes. And what happens is that if you think for yourself, how can you represent a bounding box? Well, it's essentially you can pick the top left corner and the bottom right corner of the pixel positions of the bounding box, and you have a representation. Well, you can also use top left corner and the height and width of the box, and you also have another representation. So what happens is that if you want to integrate multiple different algorithms that were implemented by other researchers and they are publicly available, you have to be sure that the data that you're using is actually consistent, and you can't simply integrate them and just assume that everything works well, because there are no standards, so everyone can use things that they want, essentially. So this an existence of a solution that integrates everything together and creates rules, and also this fragmentation that exists, leads us to believe that it would be interesting to define an architecture that actually helps the creation of a framework that is able to build a solution that depends on visual data and can then represent this information and eventually transit it to 3D. So our main objective is to further this beyond and essentially propose a novel architecture for visual scene understanding towards 3D virtual synthesis that helps the integration of different types of algorithms, providing a unified framework where different algorithms can be integrated, assuming that they follow some rules, and then the information can seamlessly be transited between blocks. So here we have a high-level overview of our proposed architecture. We have three main blocks, which are the scene analysis, scene description, and scene synthesis. Well, these blocks are associated with an algorithm selector component that will help the user essentially automatically defining which is the best algorithms to use given the specific scenario. And all these components are within a module that we call data orchestrator that has a responsibility of essentially being the coach of the entire architecture that basically defines rules and makes it that everything works flawlessly. So, starting with the scene analysis. Well, the scene analysis module is essentially responsible to extract information from visual data. So this can be from low-level features to high-level features. For instance, information about the pixel colors or the pixel positions towards things like pose estimation, object detection, masks for the image, and so on. The idea of this module is that everything that is, let's say, according to the visual data or processing visual data will be implemented within this model. And the output of this model will be essentially the, let's say, unified and according to the rules output of those algorithms. So the second module is the data description or the scene description. Well, this module receives the information from the processing of the visual information and then has the responsibility of creating a more advanced and concise representation of the information using the power of the scene graphs. So the idea is that we have information that comes from multiple different algorithms that can have some overlappings and so on. And the idea is that in this model, we will use the contextual information that is extracted from vision and a refinement process to make sure that the semantic and visual information that is extracted from the scene is well organized and well represented. We then serialize this information to form a specific scene graph that can be used for later processes. The idea of this scene graph regenerated is that not only can it be machine readable, but it can also be human readable, so that we have a specific format that we can actually interact with it and make some changes that will be progressed towards the end of the pipeline. So here we have an example of what is actually a scene graph. So essentially, a scene graph is a data structure that allows the description of objects, attributes, and their relationships, allowing a coherent and comprehensive description of visual scenes. For instance, in this image, we have a flower that is on a window, and that window is behind a cat, and the cat is on the bed. So essentially, if we look at the image on the right, we can understand what is the semantic meaning of the image without even seeing the image. This means that the information about the context and about the content of the image can be extrapolated towards a representation that can be understood both for machines and for humans. So the final module is synthesis, which is essentially responsible to create 3D content. The idea of this model would be to integrate things like synthesis refinement, let's say, how should I call it? I'm sorry, SMPL models, which are essentially parametric human 3D models that integrate essentially algorithms that generate features that represent specific parts of the joints of the human body, which we could essentially generate different avatars just measuring and changing a bit those parameters. So how can all of these can be built together? Well, the idea is that the algorithm selector and the data orchestrator are essentially the glue that makes everything work together. So the orchestrator is essentially the responsible for making sure that data flows goes from the 3 different models without any issues, and that the system knows what are the requirements of the algorithms and what is the output of each algorithm, so that they are well maintained and there is a consistency within the modules. So that, for instance, if we want to increase the processing power, or for instance, include a new algorithm for the analysis, every single other part of the pipeline will know how to use the output of that algorithm, because that would be implemented according to the rules defined by the orchestrator. The algorithm selector essentially will help decision making. So the idea is that if a user defines a specific output application, and given the input data, we could select which algorithm should be used to extract information for that. For instance, if you want to follow football players, for instance, on a match, given that the input video, we just need object detector and tracking. We shouldn't use, for instance, instance segmentation, which is not required. So the idea of this module is that it would look at what is the requirement and what is the best course of action to use in order to reduce the complexity of the system. So in order to show that this proposal can actually be used in practice, we decided to generate hybrid data for a dataset augmentation and use these ideas of the system in order to create basically a prototype that uses specific modules for all the parts. So the idea essentially is to use a YOLO object detector to detect persons. We use the Vive pose estimation algorithm to estimate the pose of a person. And we then use the SMPL model to basically pick those pose informations and the detection of the person on a specific place and generate a virtual avatar that can be replaced, can replace the human in the image. We then use inpainting to extract the human from the image and put only the avatar. So here we have an example of that. So essentially we have a person and we detect the person, estimate the pose and adapt the SMPL values. And we then insert a virtual avatar inside the same place as the person. And then we can remove the person from the image, effectively creating a hybrid data that can be used to train other models or fine-tuning. So the idea is that by using this, we can effectively create new data just using original video information or images. So another important aspect about the description of the image that is basically used on the second module is that since we do an analysis of the image and then we create a new representation that is both machine readable and human readable, we can in fact just pick that information, change it, and the entire process will just run. So in this case, we have the definition of what should have in the image, and we just addition a rotation, and the generator, the scene synthesis model automatically generates the new image according to the different attribute that is implemented. So here we have another example. For instance, we have a woman that is running towards the horizon, and we can simply swap the orientation of the person and create a video that is essentially a person running towards the image. So where can we actually use a system that implements this architecture that we defined? Well, we believe that it can be used for applications in virtual reality and augmented reality, as this helps making the transition between visual data and 3D representation more easily. And it allows the creation of new different 3D data given the modifications on the scene graph. We also believe that this can be used, for instance, to recreate or store information about surveillance according to GDPR rules, so that the face of a person is not visible and therefore there are no problems about identification. And we also believe that sports analysis can also be a good goal to use these applications. So since this is an early basically work, we believe that in order to adapt and grow a system that uses this architecture, it should be required to have an evaluation of scalability so that things like LLMs, LVMs, or even edge devices can be integrated within it seamlessly. Another important part is that real-time processing may change the integration of the algorithms within the framework, so that the data orchestrator needs to be very fast, and also the algorithm selector too. And another important aspect that we believe that needs to be worked on is the user-centric device, so that a system that integrates this ideas, needs to be able to give the user the control to know what are the algorithms that are implemented, how can they select them, and change the output manually. So, in conclusion, we show that our proposed architecture can actually be used in practice, and there are multiple research opportunities that came from it, which mean that more work can be done, and we highlight that this transition from visual scene to virtual representation can have multiple contributions depending on the stage of the system. We are also able to successfully use scene graphs for this particular application, which are in practice still not used. This is basically an open area of investigation and research, and we believe that this could heighten their usage in practice and further increase research on them. So here I have some references from the work, and thank you all for being here.